In this video we will cover an exercise which is about computing the number of electrons and also atoms in a coin of pure aluminum. We have done something similar for a copper coin in the previous video, and before you start with the exercise here you might want to refamiliarize yourselves with the concept of using the table of elements, checking for the atomic mass, finding out the number of protons in a core of a certain element, and also what mole means and also Avogadro constant. These pieces of the puzzle are required in order to solve the upcoming exercise. Please try to do this on your own before checking the solution, but if you're stuck or if you want to check your result against my solution, you will find everything linked in the video description. If you have any questions, do not hesitate to drop me a comment down below. And now it's time to start with this exercise. My name is Andreas from the Phyllis Engineer, and here we go. Now, if you have watched the video on how to compute the number of atoms in a copper coin, this one here is very similar. But the difference between the two is that the last one was an example on it which showed you how to basically compute this number, and this one here is an exercise which asks you to do the same but for a different material. So the aim of this exercise is that you can calculate the number of electrons and also atoms in a coin of pure aluminum. Before you start, you should have watched the example video on the copper coin from the last module, so you know how to use the table of elements, so you understand what Avogadro's constant is, what the unit mole actually refers to, and also the process of how to compute the number of atoms in a certain material. Please try to perform the exercise by yourself before you look at the solution, which is in the rear section of this video here. So you will be given the example solution at the end, but before you watch this, please try it on your own. Before we start, let's briefly discuss the motivation behind this exercise here. We have already talked about the importance of copper for electronics. Aluminum is similarly important. It's not used as a conductor as often as copper, but it has its applications. For example, if you look at landlines, you will find that they are made out of aluminum and not out of copper for two major reasons. The first one is weight and the second one is price. So aluminum is still a very good conductor, not as good as copper. We will get to the concept of conductivity very soon, but the major arguments for using aluminum are weight and price. So it's still one of the most important materials which you will find. And this is why it makes sense to investigate some of its properties, just as we did with copper. And the approach is the same as with the copper video. You should watch it if you haven't done so already, and then transfer the same scheme to aluminum. In order to help you a little bit and to save some time, I have given you a small extract from the table of elements, which you can find here. We have discussed copper in great depth in the last video, and we will do the same now, and you will do the same now for aluminum, which you will find here, abbreviated by AL, and you will find all the information required to conduct the exercise in this small box here. And on the next page, or in the next few seconds of the video, we will switch to the example solution, so you should pause now, compute the result by yourselves, and then resume the video to look at my solution to the problem. Okay, and here comes the sample solution to this exercise here. The first step is to determine the atomic mass from the table of elements, just as we did with the copper video. For aluminum, this is 26.982 grams per mole, so it's about half as heavy as copper and 26 or 27 times as heavy as hydrogen, for example. This is what the atomic mass tells us. And in the second step, we can use the atomic mass and also Avogadro's constant, which is a predefined number of atoms of a certain material, to determine the number of atoms in the desired amount of aluminum which we are looking at. So the number of atoms within our aluminum coin is 5.58 times 10 to the power of 22. And using this number in the third step, we can easily find the number of electrons by looking again into the table of elements, by extracting the number of protons for aluminum, and then by simply multiplying the two. So the number of atoms in the aluminum coin times the number of protons, and we know that for an uncharged element the number of electrons is identical. We can then arrive at this number here, which is the result of this exercise. So 7.254 times 10 to the power of 23 is the number of electrons contained in the aluminum coin with a weight of 2.5 grams. For now, that's all. I hope you enjoyed the video. If you have any questions, please do not hesitate to drop me a question down below in the comments. I wish you a nice day. See you next time here on The Fearless Engineer.